Picture a huge language model that needs a data center full of expensive GPUs just to run. Now, what if the exact same model could fit on your laptop or even your phone with almost no drop in quality? That is not a fantasy, it is quantization, one of the most important tricks in the whole business of deploying models. And here's the thing, the idea is almost embarrassingly simple. Store the model's numbers using fewer bits. That's it. Yet it can shrink a model 4 to 8 times over and make it dramatically faster. Let's break down how it actually works. Look, at its core, quantization is a mapping problem. We have a wide range of real, high-precision numbers, and we want to squeeze them onto a tiny grid of whole numbers. Follow the 4 steps one at a time. Start with the model's original weights, stored in high precision, usually 32 or 16-bit floating point. Each one is a rich, fine-grained number, and there are billions of them, so together they eat enormous memory and compute. This is what we want to compress. Next, we look at the range those values span and choose a scale. The scale is the single number that maps that whole real range onto a small grid of representable integers, say the 256 slots of an 8-bit format. Then round each weight to its nearest point on that grid. Every rich floating point value collapses to the closest integer slot, and this rounding step is where the compression actually happens, and also where a little error quietly creeps in. Finally, at inference time, multiply each stored integer back by the scale to recover an approximation of the original number. It is not exact, but it is close, and the heavy math in between now runs on cheap, fast integer hardware. So what do we actually gain, and what do we give up? Here are the two options laid side by side. Full precision weights are the accurate default. Every number carries 32 or 16 bits of detail, so the model behaves exactly as it was trained. The problem is size and speed. All those bits take real memory to store, real bandwidth to move, and heavier math to compute, which is why the biggest models demand data center hardware. Quantized weights use far fewer bits, commonly 8 or even 4. The model gets several times smaller, it downloads faster, less data moves through memory, and integer math runs quicker on the very same chip. The trade is a little rounding error, which, handled well, is often surprisingly hard to even notice. Strip it down, and 3 ideas capture why quantization matters so much. It stores weights in fewer bits, 8 or 4 instead of 32. That single change is what shrinks the model on disk and in memory, turning something that needed a server into something that fits on modest hardware. Cuts memory and speeds up the math. Fewer bits mean less data to shuttle around, and integer operations run faster and cheaper than floating point on most hardware, so inference gets quicker and lighter at the same time. It trades a little accuracy, and modern methods manage that trade carefully. The main danger is a few extreme outlier values stretching the grid so everything else loses resolution, which is why today's best schemes handle those outliers specially, and how for-bit quantization stays usable. Alright, let's lock in what matters. Quantization stores a neural network's numbers in fewer bits, shrinking it and speeding it up while keeping most of its original behavior intact. It works by choosing a scale that maps high-precision values onto a small integer grid, rounding each weight to the nearest point, then scaling back at inference. The payoff is deployment. A model that needed a data center GPU can run on a phone, a laptop, or a single consumer card, often with surprisingly little accuracy loss. Broadly, there are 2 families: post-training quantization, done quickly after training, and quantization-aware training, which retrains the model to tolerate it. If you like big ideas made small like this, we have a whole library of them waiting at standarity.com. Come take a look.